In this lesson, we have some more vocabulary. We're looking at tangents to a circle. And I don't want you to get confused. Yes, you've seen the word tangent before, and it dealt with trigonometry. When we're talking about a circle, a tangent is a line in the same plane as the circle that intersects the circle at exactly one point. So what you're looking at is a line that's just barely touching the circle at one point. And we call that point the point of tangency. So in this figure, you see that circle C has a line that is tangent to it with point P as the point of tangency. And in the Explore activity, they have us looking at a relationship between the radius drawn to the point of tangency and that tangent line. So they want us to measure the angle formed by the radius and the tangent line. So I'm going to go ahead and do that. And interestingly, it's a 90-degree angle. Now I'm not going to do the Explore activity entirely so that I have 3 circles, but I am going to go ahead and do one more circle. So let's say I have this circle. And here's a point on my circle, and I'm going to draw a line that passes through just this one point of the circle. Now here's the center of the circle. I know so because the compass left an indentation in my paper. And when I draw the radius to that point of tangency and measure that angle, lo and behold, it's 90 degrees. So it wants us to make a conjecture about the relationship between a tangent line and the radius to the point of tangency. The tangent line is perpendicular, remember that's the symbol for perpendicular, to the radius to the point of tangency. Remember, perpendicular means intersecting to form a 90-degree angle. It says describe any possible inaccuracies related to the tools you used in this Explore. If your compass had been wobbly and you tried to do this, you might end up with a little bit of an inaccuracy there. So here's that tangent radius theorem. If a line is tangent to a circle, then it is perpendicular to a radius drawn to the point of tangency. Let's go ahead and prove it. We're going to prove it indirectly. And when you're doing a proof indirectly, what you're starting off with is the assumption that that which you're trying to prove is false, right? So I'm going to assume that CP is not perpendicular to line M. So then that must mean that there is a point Q on line M such that CQ is perpendicular to M. And if CQ is perpendicular to M, then triangle CQP is a right triangle. And CP would have to be greater than CQ because CP would be the hypotenuse. If angle Q was my right angle, so since line M is a tangent line, it can intersect circle C at only point P, and all points of line M are in the exterior of the circle. So that would mean that point Q is in the exterior of the circle. So then that would mean that CP is less than CQ because CP is a radius of the circle. But this contradicts our original assumption that there existed a point Q such that CQ was perpendicular to M, because then that would mean CP was greater than CQ. So let me go through that one more time because I would absolutely understand if that was a little bit hazy. When we assumed that there was another point Q that would be perpendicular such that CQ would be perpendicular to M, that meant that CP would be greater than CQ. But we just showed that CP has to be less than CQ. So this is a contradiction. Therefore, our original assumption is false, and CP must be perpendicular to line M. In this reflect problem, I have a diameter, AB, and I have these two tangent lines. So what can we conclude about the tangent lines? Well, let's do a little bit of labeling here. Since L would be perpendicular to OA, and M would be perpendicular to OB, and I know OA and OB are collinear, I have two lines perpendicular to the same line. That means L must be parallel to line M. The converse of the tangent radius theorem is also true, so that if I know a line is perpendicular to a radius of a circle at a point on the circle, then I can use that to conclude that it is tangent to the circle at that point. Okay, so how could we construct tangents to a circle? Step by step. Step A says use a compass to draw a circle. So there's my circle. This point is C. Mark a point X outside the circle and use a straight edge to draw CX. So I'm going to draw X right here. There's segment CX. The next thing it says is to use our compass and straight edge to construct the midpoint of CX. So the way that we do this is by constructing the perpendicular bisector of CX. Okay, so remember, in order to do a perpendicular bisector, you need your compass setting to be a little bit more than half. And big sweepy arc from X. Big sweepy arc from C. And I could draw the line that connects those dots, and that would be my perpendicular bisector. I don't actually need the perpendicular bisector. The only thing I needed was the midpoint. So I'm just going to put the ruler back here and mark that point as my midpoint. And it says to label it M. Then it says to use a compass to construct a circle with center M and radius CM. So center M means I put the compass point there. Center CM means there's my compass setting, and then I make my circle. Last thing it says is label the points of intersection A and B. So here's A, here's B, and I can draw lines from X through A. Notice how it's tangent to the circle. Same thing, XB. How can we justify that XA or XB is a tangent line? And it gives us the hint, draw segment CA. If I draw segment CA and I draw segment CB, I could measure that angle and show that it's 90 degrees. So since the angle formed by radius CA to line AX is 90 degrees, XA is tangent to circle C by the converse of the tangent radius theorem. It says draw CA and draw CB, consider quadrilateral CAXB, state any conclusions that we can reach about the measures of angles CAXB. Well, I already drew those radii in. I know that the measure of angle CAX equals the measure of angle CBX, which is 90. I remember from a few modules ago that the sum of the interior angles of a quadrilateral equals 180. I'm sorry, not 180, 360. And since each of these is 90, so measure of angle CAX plus measure of angle CBX plus measure of angle ACB plus measure of angle AXB has to equal 360. I know each of these is 90 from up here, so 90 plus 90 is 180, plus the measure of angle ACB plus measure of angle AXB equals 360. And that allows me to conclude that the measure of angle ACB plus the measure of angle AXB has to equal 180. So I know that these two angles have to be supplementary. Gosh, it'd be convenient. I know angle ACB is called a central angle. It'd be convenient if there was some vocabulary word for angle AXB. Oh, look! Vocabulary. A circumscribed angle is an angle formed by two rays from a common endpoint that are tangent to a circle. So, there it is. A circumscribed angle of a circle and its associated central angle are supplementary. And we just saw that. So, we kind of already proved that, didn't we? I'm given that angle AXB is a circumscribed angle of circle C, and I'm trying to prove that AXB and ACB are supplementary. We already did this. Let's go through it one more time. Since it's a circumscribed angle, XA and XB are tangent to the circle. Therefore, XAC and XBC are 90 degrees by the, what was that called again? The tangent radius theorem. In quadrilateral XACB, the sum of the measures has to be 360. Since XAC and XBC have to add up to 180 because 90 plus 90 equals 180, that means AXB plus ACB is going to be 360 minus 180, which is 180. So AXB and ACB are supplementary by the definition of supplementary. So is it possible, in this reflect question, for quadrilateral AXBC to be a parallelogram? Well, let's think about what we know about a parallelogram. In a parallelogram, opposite angles are congruent, and so that would mean, well, I already know these angles are going to be congruent, but in order for these angles to be congruent, I know that they're supplementary, so that means each of them has to be 90 degrees. So The only way that this would be true is if all of the angles were all of the angles were right angles. So if all of the angles are right angles, then it would be a rectangle. Oh, but notice how these consecutive sides are congruent. So not only is it a rectangle, it would have to be a square. Yes, if AXBC is a square. In the elaborate problem, I have these two tangent lines, and they're asking us to show that Km is congruent to Kn. This is a very important property. So let's draw KC. Well, I know KC is congruent to KC by reflexive. I know that angle KMC and angle KNC are right angles by the tangent radius theorem. So triangle KMC and triangle KNC are right triangles. MC is congruent to NC because they're radii of the same circle. So triangle KMC is congruent to triangle KNC by hypotenuse leg. Since